You're tasked with building a model to classify customer churn based on a dataset with many features. You need a robust model that's efficient and can handle high-dimensional data. Which of the following algorithms would be the most suitable choice? A. Logistic regression. B. Decision tree. C. Random forest. D. Linear SVC. E. All of the above. A. Logistic regression. Logistic regression is a linear model that is suitable for binary classification problems. It can handle high-dimensional data, but its performance might degrade in the presence of complex nonlinear relationships. Correct, but not the most suitable. B. Decision tree. Decision trees are nonlinear models that can be effective for both classification and regression. They can handle high-dimensional data, but they are prone to overfitting, especially with large datasets. X20. Correct, but not the most suitable. C. Random forest. Random forest is an ensemble method that combines multiple decision trees to improve accuracy and reduce overfitting. It is generally more robust and efficient than a single decision tree, making it suitable for high-dimensional data. X20. Correct, but not the most suitable. D. Linear SVC. Linear SVC is a linear model specifically designed for classification tasks, offering good performance with high-dimensional data. It handles large datasets efficiently, making it a good choice for customer churn prediction. X20. Correct, but not the most suitable. E. All of the above. While linear SVC is particularly well suited for high-dimensional data, all the listed algorithms can be effective for customer churn prediction. The choice depends on factors like the dataset's characteristics, desired model complexity, and interpretability requirements. Correct and most suitable. E. All of the above. Linear SVC strengths and use cases. Linear SVC is a powerful algorithm with several benefits. High-dimensional data. Linear SVC handles datasets with many features efficiently, making it ideal for complex scenarios like customer churn prediction. X20. Robustness. It is generally less prone to overfitting compared to nonlinear models like decision trees. X20. Efficiency. Linear SVC is known for its speed and ability to handle large datasets. X20. Real-time use cases. Customer churn prediction. Building a model to identify customers likely to stop using a service. X20. Fraud detection. Identifying fraudulent transactions or activities in financial systems. X20. Image classification. Categorizing images based on their content, often used in image recognition tasks. Imagine you're working for a telecommunications company and want to predict which customers might cancel their service. You have a dataset with hundreds of features, like customer demographics, service usage patterns, and billing history. Linear SVC would be an excellent choice to build a churn prediction model that handles this high-dimensional data efficiently and effectively. Logistic regression. Logistic regression is a widely used linear model for binary classification. It predicts the probability of an event occurring. Example: a customer churning. Let's say you have a dataset with customer information, including age, income, and internet usage. You want to build a model to predict if a customer will buy a new phone or not. Logistic regression can be used to model the probability of a customer purchasing a phone, based on their characteristics. Decision tree. Decision trees are nonlinear models that use a series of rules to classify data. They are easy to interpret and visualize, making them useful for understanding the decision process. Consider a scenario where you want to classify customers based on their spending habits. You can use a decision tree to create a series of rules, like if customer spending is above 500, then categorize them as high spenders. This helps you segment customers based on their spending patterns. Random forest. Random forest is an ensemble method that combines multiple decision trees to create a more accurate and robust model. It is generally less prone to overfitting than individual decision trees. In the customer spending example, instead of relying on a single decision tree, you can use a random forest to combine multiple trees, each trained on different subsets of the data. This ensemble approach helps improve accuracy and prevent overfitting. Which of the following statements is true about the linear SVC class in sklearn? A linear SVC implements a linear kernel SVM using a 1vs1 strategy for multi-class classification. B. Linear SVC uses a stochastic gradient descent (SGD) optimizer for training. C. Linear SVC is suitable for large data sets due to its efficient training time. D. All of the above. A linear SVC implements a linear kernel SVM using a 1vs1 strategy for multi-class classification. This statement is true. Linear SVC utilizes a linear kernel, which means it finds a hyperplane that separates data points into classes. For multi-class problems, it employs a 1vs1 strategy, creating a binary classifier for each pair of classes. This is a common approach for multi-class SVM classification. True. B. Linear SVC uses a stochastic gradient descent (SGD) optimizer for training. This statement is true. Linear SVC relies on the stochastic gradient descent (SGD) algorithm for training. SGD is an iterative optimization method where model parameters are updated based on gradients calculated from a small batch of data points. This makes the training process efficient, especially for large data sets. True. C. Linear SVC is suitable for large data sets due to its efficient training time. This statement is true. Linear SVC is generally well suited for large data sets because of its efficient training time. The use of SGD allows it to process data in batches, reducing the computational cost and memory requirements compared to traditional quadratic programming approaches used in some SVM implementations. True. D. All of the above. This statement is true as all the previous statements are correct. True. D. All of the above. Linear kernel. A linear kernel in SVM calculates the dot product between data points. This results in a linear decision boundary, which is a straight line or hyperplane that separates data points into different classes. Imagine you have data points representing customer spending habits, example income, age, and you want to classify them as high spenders or low spenders. A linear kernel could be used to find a line that separates these two groups in the income-age space. The line would be a linear decision boundary. Linear kernels are suitable for problems where the data is linearly separable, meaning a straight line or plane can easily divide the classes. 1vs1 strategy. This strategy is used in multi-class classification problems. It involves training a separate binary classifier for each pair of classes. For example, if you have three classes A, B, C, you would train three binary classifiers A versus B, A versus C, and B versus C. Let's say you are classifying images of animals into three categories: cats, dogs, and birds. 1vs1 strategy would train three binary classifiers: cat versus dog, cat versus bird, and dog versus bird. This strategy is often chosen for multi-class SVM problems because it can be more efficient than other methods like 1vs rest, especially when the number of classes is large. Stochastic gradient descent (SGD). SGD is an iterative optimization algorithm used in machine learning to minimize a loss function. It updates model parameters by taking small steps in the direction of the negative gradient, which is calculated from a small batch of data points. Imagine you are trying to find the optimal values for the weights of a linear regression model. SGD starts with random weights and then repeatedly updates them by calculating the gradient slope of the loss function based on a few data points at a time. The updates are made in the direction that reduces the loss, gradually moving the model towards the optimal weights. SGD is widely used in machine learning due to its efficiency, especially for large data sets where computing the gradient over the entire dataset can be computationally expensive. What is the primary objective of linear SVR in sklearn? A. To classify data points into distinct categories. B. To predict a continuous target variable using a linear model. C. To perform dimensionality reduction on high-dimensional data. D. To identify clusters of similar data points. A. To classify data points into distinct categories. False. Linear SVR is designed for regression, which focuses on predicting continuous values. Classification tasks involve categorizing data into distinct groups. This choice describes the goal of classification algorithms, not linear SVR. B. To predict a continuous target variable using a linear model. True. This is the accurate description of linear SVR's purpose. It utilizes a linear model to find a hyperplane that best fits the data, enabling it to predict continuous target values based on input features. C. To perform dimensionality reduction on high-dimensional data. False. Dimensionality reduction techniques aim to reduce the number of features in a dataset. While linear SVR can handle high-dimensional data, its primary function is not to reduce dimensionality. This task is handled by algorithms like principal component analysis (PCA). D. To identify clusters of similar data points. False. Clustering algorithms are used to group data points based on similarities. Linear SVR is focused on predicting a continuous output, not on grouping data points into clusters. This choice describes the objective of clustering algorithms, not linear SVR. B. To predict a continuous target variable using a linear model. Linear regression. A statistical method used to predict a continuous target variable based on a linear relationship with input features. The goal is to find the best fitting line or hyperplane in higher dimensions that minimizes the difference between predicted and actual values. It's widely used for tasks like predicting housing prices, sales forecasting, and trend analysis. Suppose you want to predict the price of a house based on its size in square feet and the number of bedrooms. You can use linear regression to find a linear equation that relates size and number of bedrooms to the house price. For example, if you have data for 10 houses, you might find the equation price 100, size 50,000, bedrooms 100,000. This equation can then be used to predict the price of new houses based on their size and number of bedrooms. Support vector machines (SVM). A powerful machine learning algorithm for both classification and regression tasks. SVMs aim to find an optimal hyperplane that separates data points in a multidimensional space. The hyperplane maximizes the margin between data points belonging to different classes in classification or minimizes the error between predicted and actual values in regression. Imagine you have data on different types of flowers, example roses, lilies, sunflowers, based on features like petal width and length. An SVM can be used to create a hyperplane that separates these flower types. The hyperplane is positioned to maximize the distance between the closest points of different flower types, making the classification more robust. Hyperplane: a decision boundary in a multidimensional space used by SVM to separate data points. In a 2D space, it's a line, and in a 3D space, it's a plane. The hyperplane is positioned to optimize the separation of data points belonging to different classes or to minimize the error between predicted and actual values. It acts as a decision rule to classify new data points based on their location relative to the hyperplane. Consider a 2D space with data points representing two types of animals, example cats and dogs, based on their weight and height. The SVM finds a line hyperplane that best separates the cats from the dogs. New animals can then be classified as cats or dogs based on their location relative to this line. Predicting housing prices. Linear SVR can be used to predict house prices based on features like location, size, number of bedrooms, and amenities. This can be helpful for real estate agents, buyers, and sellers to make informed decisions about property value. Stock market forecasting. Linear SVR can be employed to predict future stock prices based on historical data, market indicators, and other relevant factors. This can be useful for investors, traders, and financial analysts to make investment decisions. Which of the following statements accurately describes the new SVC classifier in sklearn? A new SVC is a linear SVM algorithm that utilizes a hyperparameter nu to control the number of support vectors. B. New SVC employs a nonlinear kernel function to map data into a higher dimensional space, allowing for complex decision boundaries. C. New SVC is a versatile SVM algorithm that can be used for both classification and regression tasks. D. All of the above. A new SVC is a linear SVM algorithm that utilizes a hyperparameter nu to control the number of support vectors. This statement is partially correct. New SVC does utilize the new hyperparameter, but it's not limited to linear SVMs. It can also work with nonlinear kernels. A new SVC is a linear SVM algorithm that utilizes a hyperparameter nu to control the number of support vectors. B. New SVC employs a nonlinear kernel function to map data into a higher dimensional space, allowing for complex decision boundaries. This statement is true. New SVC can leverage nonlinear kernels, like the RBF kernel, to handle intricate data distributions and create flexible decision boundaries. B. New SVC employs a nonlinear kernel function to map data into a higher dimensional space, allowing for complex decision boundaries. C. New SVC is a versatile SVM algorithm that can be used for both classification and regression tasks. This statement is also true. New SVC's flexibility allows it to be used for both classification and regression problems, making it a versatile tool. New SVC is a versatile SVM algorithm that can be used for both classification and regression tasks. D. All of the above. Since A, B, and C are all accurate statements, the correct answer is D. All of the above. D. All of the above. D. All of the above. Support vector machines SVMs. SVMs are powerful supervised learning models used for both classification and regression. Their core principle lies in finding the optimal hyperplane that maximizes the margin between data points of different classes. SVMs are supervised learning models that excel in classification and regression tasks by finding the optimal hyperplane that maximizes the margin between data points of different classes. Kernel functions. Kernel functions allow SVMs to model nonlinear relationships by transforming data into a higher dimensional space. Popular kernels include linear, polynomial, and radial basis function RBF kernels. Kernel functions enable SVMs to model nonlinear relationships by transforming data into a higher dimensional space. Common kernels include linear, polynomial, and radial basis function RBF kernels. Hyperparameter new. The new hyperparameter in new SVC plays a crucial role in controlling the number of support vectors and the upper bound on the fraction of training errors. It offers a mechanism to balance model complexity and generalization ability. The new hyperparameter controls the number of support vectors and the upper bound on the fraction of training errors allowed. It provides a mechanism to balance model complexity and generalization ability. Image classification. New SVC is a suitable choice for image classification tasks, especially when dealing with complex features and patterns. It can learn intricate relationships within image data to achieve accurate classification. New SVC is well suited for classifying images with complex features and patterns. Text classification. New SVC can handle text classification tasks effectively, such as sentiment analysis or topic categorization, by employing sophisticated kernels to capture the nuances of textual data. New SVC can be used for tasks like sentiment analysis or topic categorization, handling text data with sophisticated kernels. Bioinformatics. New SVC finds applications in bioinformatics for analyzing genomic data, classifying proteins, and predicting drug responses. Its ability to handle complex data and identify patterns makes it a valuable tool in this field. New SVC finds applications in analyzing genomic data, classifying proteins, and predicting drug responses. Let's assume we have a dataset with features x1, 2, 2, 3, 3, 1, 4, 4, and corresponding class labels y0, 0, 1, 1. We can use new SVC to build a classifier that separates these points based on their class. From sklearn.svm import new SVC. x1, 2, 2, 3, 3, 1, 4, 4. y0, 0, 1, 1. Model new svno 0.5, kernel erb. Model.fit x, y. Now, we can predict the class of a new data point. New data point 2.5, 2.5. Prediction model.predict new data point. Print prediction. Which of the following statements is true about new SVR? A new SVR is an advanced regression technique that prioritizes maximizing the margin of separation, making it ideal for complex and high-dimensional data. B. It is often used to address overfitting problems in regression models, especially when dealing with large datasets or limited data points. C. Unlike standard SVR, new SVR directly controls the number of support vectors, promoting more efficient model training and reduced complexity. D. All of the above. A new SVR is an advanced regression technique that prioritizes maximizing the margin of separation, making it ideal for complex and high-dimensional data. True. New SVR, similar to support vector machines SVMs, prioritizes maximizing the margin between data points belonging to different classes. This is especially beneficial for complex and high-dimensional datasets where clear boundaries are hard to define. B. It is often used to address overfitting problems in regression models, especially when dealing with large datasets or limited data points. True. New SVR's focus on margin optimization helps mitigate overfitting. It prevents the model from being overly influenced by outliers, improving generalization capabilities, especially in cases of large datasets or limited data points. C. Unlike standard SVR, new SVR directly controls the number of support vectors, promoting more efficient model training and reduced complexity. True. New SVR directly controls the number of support vectors through the new parameter. This allows for more efficient training and reduces the complexity of the model, as it needs to manage fewer support vectors compared to standard SVR. D. All of the above. True. All the statements A, B, and C are accurate descriptions of new SVR's characteristics and benefits. D. All of the above. These are the data points that lie closest to the decision boundary and have a significant impact on the model's predictions. Consider a dataset with two classes cats and dogs. The support vectors would be the cat and dog images that are most difficult to classify correctly, sitting right on the boundary between the two classes. The model uses these critical points to create the decision boundary. The distance between the decision boundary and the nearest data points support vectors. A larger margin generally indicates a more robust model. Imagine you have a line separating cats from dogs. The margin is the distance between the line and the closest cat or dog image. A larger margin implies the line is further away from the data, indicating a more confident and less prone to misclassification. A parameter that controls the fraction of support vectors and the width of the margin, directly affecting the model's complexity and performance. A lower new value will result in fewer support vectors and a wider margin, leading to a simpler model with potentially less accuracy on the training data but better generalization to unseen data. A higher new value might have more support vectors and a narrower margin, potentially achieving higher accuracy on the training data but being more susceptible to overfitting. Transform data into a higher dimensional space to identify nonlinear relationships between data points, improving model accuracy. Imagine you have data that cannot be separated linearly. A kernel function can transform the data into a higher dimensional space where it can be separated with a linear boundary. This allows the model to capture complex nonlinear relationships. Helps prevent overfitting by adding a penalty term to the loss function, encouraging the model to be simpler and generalize better to new data. Regularization acts like a constraint on the model's complexity. It penalizes models that are too complex and have too many parameters. This encourages the model to find simpler solutions that generalize well to unseen data. Selecting the optimal values for parameters such as new, kernel, and regularization strength to achieve the best possible model performance. Imagine you have a new SVR model with different possible values for the new parameter. You can try different values for new example 0.1, 0.5, 0.9 and evaluate the model's performance on a validation set. The new value that leads to the best performance on the validation set is the optimal value for the model. Python. From sklearn.svm import new SVR. Initialize the new SVR model with desired parameters. Model new SVR new 0.5, kernel erb, C 1.0. Fit the model to your training data. Model.fit strain, train. Make predictions on new data. epred model.predict stist. This code snippet demonstrates how to implement new SVR in Python using the sklearn library. You first initialize the model with desired parameters like new, kernel type, and regularization strength. Then you fit the model to your training data and make predictions on new data. Time series forecasting. Predicting future values based on historical data, such as stock prices, weather patterns, or sales trends. New SVR can be used to model the underlying patterns in time series data and make predictions about future values. Image recognition. Classifying images by identifying patterns and features within them. New SVR can be used to learn complex patterns from images and classify them into different categories, such as identifying different types of objects, recognizing faces, or detecting anomalies. Natural language processing (NLP). Analyzing text data to extract insights, perform sentiment analysis, or translate languages. New SVR can be used to learn the relationships between words and phrases in text data and perform various NLP tasks, such as sentiment classification, topic modeling, and machine translation. Financial modeling. Predicting market trends, asset prices, or risk assessments. New SVR can be used to model the complex relationships between financial variables and make predictions about future market behavior, asset prices, or credit risk. Which of the following are valid use cases for scikit-learn's one-class SVM? A. Anomaly detection in time series data. B. Image classification. C. Fraud detection in financial transactions. D. All of the above. Correct. One-class SVM excels at identifying anomalies in time series data where the majority of data points represent a typical pattern, and you want to detect unusual or outlier instances. Example: suppose we are monitoring network traffic. We have a series of data points representing network traffic volume over time. Using one-class SVM, we can identify unusual spikes in traffic volume, which could potentially indicate a denial of service attack or other network anomalies. Anomaly detection in time series data, identifying unusual patterns or spikes in sensor readings, network traffic, or financial data. Correct. One-class SVM, while not the primary tool for multi-class image classification, can be effective for outlier detection in image data. It can identify images that deviate significantly from the norm, such as images with blurred objects or distortions. Example: in a manufacturing process, one-class SVM can detect defective products in a batch of images. If most images depict a standard product, a few images with anomalies, blurry, distorted, or missing parts can be identified using one class SVM. Image classification, identifying images that don't belong to a particular class, such as detecting defective products in a manufacturing process. Correct. One class SVM is a valuable tool for detecting fraudulent financial transactions. It identifies transactions that significantly deviate from typical spending patterns. Example: consider a dataset of credit card transactions. One class SVM can identify transactions that are unusual in terms of amount, location, or timing, potentially indicating fraudulent activity. Fraud detection in financial transactions, detecting suspicious transactions that deviate from typical spending patterns. Correct. Based on the explanations for A, B, and C, one class SVM is indeed effective for all the mentioned use cases: anomaly detection in time series data, image classification, specifically outlier detection, and fraud detection in financial transactions. One class SVM, also known as outlier detection, is a machine learning algorithm that aims to identify data points that are significantly different from the rest of the data. D. All of the above. One class SVM, also known as outlier detection, is a machine learning algorithm that aims to identify data points that are significantly different from the rest of the data. It is particularly useful when you have a dataset where the majority of data points represent a normal or expected behavior, and you want to detect unusual or outlier instances. One class SVM, also known as outlier detection, is a machine learning algorithm that aims to identify data points that are significantly different from the rest of the data. It is particularly useful when you have a dataset where the majority of data points represent a normal or expected behavior, and you want to detect unusual or outlier instances. Anomaly detection is a task in data mining that aims to identify data points that deviate significantly from the rest of the data. These outliers can be indicative of unusual or unexpected behavior, and their identification can be crucial for various applications, such as fraud detection, system monitoring, and healthcare. Anomaly detection in time series data, identifying unusual patterns or spikes in sensor readings, network traffic, or financial data. Fraud detection in financial transactions, detecting suspicious transactions that deviate from typical spending patterns. Image classification, identifying images that don't belong to a particular class, such as detecting defective products in a manufacturing process. Time series data is a sequence of data points collected at successive timestamps. Each data point represents a measurement or observation made at a specific time. Examples of time series data include stock prices, weather data, sensor readings, and website traffic patterns. Anomaly detection in time series data, identifying unusual patterns or spikes in sensor readings, network traffic, or financial data. Fraud detection involves identifying fraudulent activities in financial transactions or other domains. This is often achieved by analyzing patterns in data to detect deviations from normal behavior that may indicate fraudulent activity. Fraud detection in financial transactions, detecting suspicious transactions that deviate from typical spending patterns. Financial transactions refer to the exchange of money or other financial instruments between individuals, organizations, or financial institutions. These transactions can involve a variety of activities, such as buying and selling goods and services, making payments, transferring funds, and investing. Fraud detection in financial transactions, detecting suspicious transactions that deviate from typical spending patterns. Image classification is a computer vision task that involves assigning labels to images based on their content. This is used in various applications, such as object recognition, scene understanding, and image retrieval. Image classification, identifying images that don't belong to a particular class, such as detecting defective products in a manufacturing process. While it is not the primary tool for traditional image classification where you have multiple classes, it can be used for outlier detection in image data. For example, identifying images that contain anomalies like blurred or distorted objects. Which of the following statements are true regarding the SVC support vector classifier in scikit-learn? A SVC is a linear model, capable of handling only linearly separable data. BSVC utilizes the concept of finding a hyperplane that maximizes the margin between classes. CSVC can be extended to handle nonlinearly separable data using kernel functions. DSVC is sensitive to scaling of features, and it's often recommended to standardize data before using SVC. Correct. In its basic form, SVC is a linear model. It aims to find a hyperplane that separates data points belonging to different classes. However, SVC can be extended to handle nonlinearly separable data using kernel functions, as explained in option C. This makes the statement partially true, but the emphasis on handling only linearly separable data makes it incorrect. Concept 1: Linear separability. SVC, in its basic form, assumes that data points belonging to different classes can be separated by a hyperplane. This means that data can be classified linearly. Image classification with simple features like color histograms. Correct. This is a core principle of SVC. By maximizing the margin between classes, SVC aims to create a robust decision boundary, making it less susceptible to noise and outliers. Concept 2: Maximum margin. SVC aims to find the hyperplane that maximizes the distance margin between the closest data points of different classes. This ensures robustness and better generalization. Object detection, where the distance between the object and non-object pixels is maximized. Correct. Kernel functions are a powerful mechanism in SVC. They map data into a higher dimensional space, transforming nonlinearly separable data into linearly separable data. This allows SVC to handle complex patterns. Concept 3: Kernel functions. SVC can be extended to handle nonlinearly separable data using kernel functions. These functions project data into higher dimensional spaces, potentially making it linearly separable. Text classification, where features are not linearly separable using word embeddings. Correct. SVC is sensitive to the scale of features. Features with larger scales can disproportionately influence the decision boundary. Standardizing data brings all features to a similar scale, preventing bias and improving model performance. Concept 4: Feature scaling. SVC is sensitive to the scale of features. Standardizing or normalizing the features is crucial for optimal performance. This ensures that features with larger scales don't dominate the decision boundary. Time series analysis, where features have varying scales using normalization. All of the above. Which of the following parameters is used to control the complexity of the decision boundary in sklearn's SVC? A. Kernel. B. C. C. Gamma. D. All of the above. The kernel parameter determines the type of kernel function used. It doesn't directly control the complexity of the decision boundary, but it defines the shape of the decision boundary, allowing for linear or nonlinear separation. It is a fundamental parameter that influences the model's capability to learn complex relationships. False. The C parameter, also known as the regularization parameter, directly controls the complexity of the decision boundary. A higher C value leads to a smaller margin more complex decision boundary with fewer misclassifications, while a lower C value results in a larger margin simpler decision boundary with more misclassifications. This parameter balances the trade-off between fitting the training data well and preventing overfitting. True. The gamma parameter is primarily used with the RBF kernel. It influences the width of the Gaussian kernel, which controls the influence of each data point. A smaller gamma value results in a wider influence, creating a smoother decision boundary, while a larger gamma value leads to a narrower influence, creating a more complex decision boundary. True. All three parameters, kernel, C, and gamma, play a significant role in shaping the complexity of the decision boundary. The kernel determines the type of decision boundary, while C controls the trade-off between margin and misclassification, and gamma influences the RBF kernel's width. These parameters work in conjunction to determine the model's ability to find optimal decision boundaries. True. D. All of the above. The decision boundary is the line or surface that separates different classes in a machine learning model. A complex decision boundary can have many twists and turns, while a simple boundary is smoother. In a binary classification problem, the decision boundary separates the positive class from the negative class. For example, in a spam detection model, the decision boundary divides emails into spam and non-spam categories. Imagine a loan approval system that uses a machine learning model to classify applicants as high risk or low risk. The decision boundary would separate applicants based on various factors like income, credit score, and loan amount. A complex decision boundary might account for intricate interactions between these factors, potentially leading to more accurate classifications but increasing the risk of overfitting. A simpler decision boundary might be more robust but might miss subtle patterns in the data. A kernel function transforms the data into a higher dimensional space, enabling the creation of nonlinear decision boundaries. Linear kernels only work for linearly separable data, while nonlinear kernels, like RBF, and polynomial kernels, allow for more flexible decision boundaries that can handle complex data patterns. Consider a cancer detection model that uses a machine learning algorithm to classify cells as cancerous or benign based on various features. If the data is linearly separable, a linear kernel might suffice. However, if the relationship between features and cancer risk is nonlinear, a nonlinear kernel like RBF would be necessary. This kernel would project the data into a higher dimensional space where it might become linearly separable, allowing the model to learn complex patterns and make accurate classifications. Regularization is a technique used in machine learning to prevent overfitting by adding a penalty term to the loss function. This penalty encourages simpler models, reducing the risk of the model memorizing the training data. Regularization helps to improve the model's generalization performance on unseen data. Imagine a stock market prediction model that uses a machine learning algorithm to predict future stock prices based on past trends. Overfitting can occur if the model learns the historical data too well, resulting in poor predictions on future data. Regularization helps to prevent overfitting by penalizing complex models, encouraging the model to learn more general patterns from the data. This helps to improve the model's ability to make accurate predictions on unseen data. Overfitting occurs when a model learns the training data too well, resulting in poor performance on unseen data. This happens when the model is too complex for the given data, leading it to memorize the training examples instead of learning generalizable patterns. Overfitting is a common problem in machine learning, and it can significantly impact the model's effectiveness. Consider a spam detection model that uses a machine learning algorithm to classify emails as spam or non-spam. Overfitting can occur if the model learns the specific characteristics of the training spam emails too well. This can lead to the model misclassifying legitimate emails as spam because it has memorized the training data. Overfitting can result in a high accuracy on the training data but poor performance on unseen emails. Image classification. Identifying objects in images, such as faces, cars, or animals. SVMs are well suited for handling high-dimensional image data. Text classification. Categorizing text documents, such as spam detection, sentiment analysis, or topic modeling. SVMs can effectively handle textual features, often represented as bag of words or TF-IDF vectors. Bioinformatics. Analyzing biological data, such as protein classification, gene expression analysis, and disease prediction. SVMs excel in handling complex, high-dimensional biological data sets. Financial modeling. Forecasting stock prices, detecting fraudulent transactions, and predicting credit risk. SVMs can effectively capture nonlinear relationships in financial data. You want to predict the price of a house based on its size and location. Which of the following parameters is used to adjust the margin of error for the model in scikit-learn's SVR? AC. B gamma. C kernel. D epsilon. AC. C is the regularization parameter in SVR. It controls the trade-off between model complexity and fitting the training data. It doesn't directly adjust the margin of error. False. B gamma. Gamma is the kernel coefficient in SVR. It determines the influence of each data point in the kernel function. It's not involved in setting the margin of error. False. C kernel. The kernel function in SVR defines how the similarity between data points is calculated. It doesn't control the margin of error. False. D epsilon. Epsilon in SVR is a hyperparameter used to control the margin of error. The model aims to minimize the error within this margin. Choosing an appropriate epsilon value balances model complexity and accuracy. True. D epsilon. Support vector regression SVR. SVR is a machine learning algorithm that uses support vectors to fit a regression model. It's suitable for predicting continuous values, such as house prices. 1. Financial forecasting, predicting stock prices, exchange rates, and other financial indicators. 2. Demand prediction, estimating product demand for inventory management and pricing strategies. 3. Energy consumption, forecasting energy consumption in buildings or industries. 4. Machine learning, training models for regression tasks in various domains. Let's say we have the following data for house prices and their sizes in square feet. Size SQ foot price 1,500, 250,000, 2,300,000, 2,500, 350,000. We can use SVR to predict the price of a house with a size of 2,200 square feet. The model would find the best hyperplane align in this case that minimizes the error within a margin specified by epsilon. Hyperparameters. Hyperparameters in SVR are parameters that control the learning process of the model. They need to be set before training. Some common hyperparameters are C, gamma, kernel, and epsilon. None. C, regularization parameter, controls the trade-off between model complexity and fitting the training data. C is a regularization parameter that controls the trade-off between model complexity and fitting the training data. A higher value of C means a more complex model that fits the training data better but may overfit. A lower value of C means a simpler model that may not fit the training data as well but may generalize better to unseen data. None. Gamma kernel coefficient determines the influence of each data point in the kernel function. Gamma is the kernel coefficient that determines the influence of each data point in the kernel function. A higher value of gamma means that each data point has a strong influence, leading to a more complex model. A lower value of gamma means that each data point has a weaker influence, leading to a simpler model. None. Kernel function used to calculate the similarity between data points. The kernel function in SVR defines how the similarity between data points is calculated. The choice of kernel function can impact the model's performance. Common kernel functions include linear, polynomial, and radial basis function RBF. None. Epsilon, margin of error allowed for each data point. Epsilon in SVR is a hyperparameter that defines the margin of error allowed for each data point. The model aims to minimize the error within this margin. A higher value of epsilon allows for larger errors, leading to a simpler model. A lower value of epsilon allows for smaller errors, leading to a more complex model. None. If we set epsilon 0.1, the model will try to predict the price of each house within a margin of 10 of the actual price. If the predicted price is within this margin, the error is considered acceptable. This allows for some flexibility in the predictions. Scikit-learn sklearn. Scikit-learn sklearn is a popular Python library for machine learning. It provides a wide range of algorithms and tools for data analysis, including SVR. None. SVR implementation. Here's how to implement SVR using scikit-learn. None. Model evaluation. After training the SVR model, we can evaluate its performance using various metrics, such as mean squared error MSE. None. We can calculate the MSE using the mean squared error function from scikit-learn. A lower MSE indicates better model performance. What is the significance of the L1 minc parameter in the sklearn.svm.svc class, and how does it impact model selection? A L1 Minc sets the minimum value for the regularization parameter C during grid search, preventing overly complex models. B L1 Minc determines the initial value of C for the optimization process, affecting the starting point of the search. C L1 Minc is used in conjunction with L1 regularization to control the sparsity of the model, leading to feature selection. D. All of the above. True. L1 Minc acts as a lower bound for the C parameter during grid search, ensuring that the search doesn't explore excessively high C values. High C values indicate weak regularization, leading to complex models prone to overfitting. By setting a minimum C, we constrain the search to values that promote a better balance between model complexity and generalization ability. Regularization. True. The L1 Minc parameter also determines the starting point of the optimization process for finding the best C value. This initial value influences the search direction and can impact the overall convergence speed of the optimization algorithm. Hyperparameter optimization. True. When L1 regularization is used in conjunction with SVC, the L1 Minc parameter helps control the sparsity of the resulting model. Lower values of L1 Minc encourage greater sparsity, effectively leading to feature selection by pushing less relevant features towards zero coefficients. L1 regularization lasso. True. All the choices A, B, and C accurately describe the significance of the L1 Minc parameter. It functions as a minimum value constraint during grid search, sets the initial C value, and plays a crucial role in sparsity control with L1 regularization. Grid search. D. All of the above. Regularization. Regularization techniques, such as L1 and L2 regularization, are used in machine learning to prevent overfitting by adding a penalty term to the loss function. This penalty discourages the model from assigning excessively large weights to features, thus improving generalization performance. Preventing overfitting in linear regression models for predicting house prices, leading to more accurate predictions on unseen data. Stabilizing image classification models by reducing the impact of noisy features, resulting in more robust models. L1 regularization lasso. L1 regularization adds a penalty proportional to the absolute value of the model's coefficients. It encourages sparsity by driving irrelevant feature coefficients towards zero, effectively performing feature selection. Identifying key factors contributing to customer churn in a telecommunications company, allowing targeted interventions. Selecting the most informative genes for disease prediction in medical diagnostics, leading to more accurate and efficient models. L2 regularization ridge. L2 regularization adds a penalty proportional to the square of the model's coefficients. It shrinks coefficients towards zero, preventing overfitting and improving stability, but doesn't necessarily eliminate features. Improving the accuracy of forecasting financial market trends by reducing the impact of noisy data. Stabilizing sentiment analysis models for predicting customer reviews, leading to more consistent and reliable results. Grid search. Grid search is a hyperparameter optimization technique that involves exhaustively searching over a predefined set of parameter values to find the best combination for a model. It systematically evaluates each possible combination and selects the one that achieves the highest performance. Finding the optimal regularization strength C in a logistic regression model for predicting customer purchase probability. Tuning the learning rate and number of hidden layers in a neural network for image recognition, improving model accuracy and efficiency. Hyperparameter optimization. Hyperparameter optimization involves tuning the parameters of a machine learning model that are not directly learned from the data. These parameters control the learning process itself, influencing the model's performance. Optimizing the number of trees and depth of each tree in a random forest model for fraud detection, improving accuracy and speed. Adjusting the kernel parameters in a support vector machine SVM model for text classification, leading to more accurate and robust models. Suppose we're using an SVC model with L1 regularization to predict credit card fraud. Our data includes features like transaction amount, time of day, and location. We set L1 minc to 0.1. During grid search, the algorithm evaluates different values of C within the range defined by L1 minc 0.1 and above. By enforcing this lower bound, we prevent the selection of models with extremely high C values, which could result in overfitting. Additionally, the L1 minc value of 0.1 impacts the initial C value for optimization, potentially influencing the convergence speed of the process. Finally, the L1 regularization, coupled with the L1 minc parameter, will drive less relevant features like transaction amount or location towards zero coefficients, ultimately leading to a sparse model that highlights the most informative features for fraud detection.